So, what does it really mean to measure time? I mean, on the surface, it's pretty simple, right? It's just a number on a clock. But if you dig down to the fundamental level of reality, you find out that time plays two completely different roles. One is, predictable and straightforward. The other, well, the other is a whole lot stranger. So today, let's dive into this duality of timing. Okay, so how do you win a race? The answer seems pretty obvious, doesn't it? You cover a set distance in the least amount of time. Simple. And this whole act, just using a clock to see who wins, it's really the most basic way we think about timing. But, and this is the cool part, it turns out that scientists use this exact same principle to probe the very nature of matter itself. Yeah, you heard that right. Scientists use the exact same idea, but they do it on an unbelievably tiny scale. They build these microscopic racetracks for the fundamental particles of matter. And just by seeing who wins the race, they can figure out a particle's most basic properties, like its mass, with just incredible precision. And this amazing piece of kit is what makes it happen. It's called a time-of-flight mass spectrometer. And its whole job, its entire purpose, is to stage a race for molecules and ions. Seriously, that's it. And just by clocking their finish times, it can sort them and figure out what they are with just astonishing precision. Okay, so to really get how this works, we first have to put on our classical physics hat. Let's step into that world for a minute. In this world, everything is predictable. I mean, think of billiard balls rolling across the table. You know exactly where they're going to go. And in this view, time is just a number on a stopwatch. Nice and simple. So in this world of classical mechanics, everything follows what's called a classical trajectory, basically a predictable path. A great example is a planet orbiting the sun, right? If you know where it starts and how fast it's going, you can calculate exactly where it will be 100, even 1,000 years from now. There's zero uncertainty, no guesswork. And inside our spectrometer, for now, this classical view totally holds up. Each little particle follows this perfect calculable arc, kind of like a tiny cannonball being fired. There's no guesswork at all. Its path is so well defined that we can predict its arrival time down to the nanosecond. But what actually determines its speed? Well, there's a really great analogy for this called the potential lake. Just imagine a particle's total energy is fixed, kind of like the water level of a lake. Now, if that particle drops into a deep valley, what we call potential energy, its kinetic energy, which is just its speed, has to increase to keep that total energy constant. So the deeper the valley, the faster the particle zips along. All right, so here's how the whole classical racetrack works, step by step. First up, we give the molecules an electric charge. Then, an electric field acts like a starting gun, and bam! It gives every single particle the exact same amount of kinetic energy, the same push. After that, they just coast. And since they all have the same energy, it's pretty simple. The lighter particles just naturally go faster. They pull ahead and reach the detector first. It's just a beautiful, elegant way to sort things by mass. But that beautiful, predictable world, it just completely shatters the moment we zoom in. And now, welcome to the quantum realm. Down here, particles are not solid billiard balls anymore. They behave like these fuzzy, uncertain waves. And it's here that our simple stopwatch starts to reveal something profoundly strange about the nature of reality itself. You see, the classical view works perfectly when you're dealing with trillions of particles all at once. But what's the reality for just one single, solitary particle on that racetrack? Well, the answer to that question, it changes everything. Okay, so down at the quantum level, our little racer isn't a point anymore. It's something called a wave packet, which is basically a fuzzy cloud of probability. It doesn't have one single location or one single speed, just a whole range of possibilities. It's kind of everywhere and nowhere all at once, with just a higher chance of being found in certain spots. Weird, right? In this comparison, this is really the heart of the matter. The classical particle, our billiard ball, has a solid, predictable path. But the quantum particle, it's a cloud of potential that actually spreads out as it travels. Its position gets more and more uncertain over time. This built-in fuzziness is what the famous Heisenberg uncertainty principle is all about. It basically says there's a fundamental trade-off baked into the universe. The more precisely you know a particle's position, the less precisely you can possibly know its momentum, how fast it's moving. And this isn't because our tools aren't good enough. It's a non-negotiable rule of nature. So, okay, we've got ourselves a paradox.
On one hand, we have this world of fuzzy, spreading waves down at the quantum level. But on the other, we have a world of sharp, predictable billiard balls in our labs. So the big question is, how do we get from one to the other?
Yeah, this is really the million-dollar question, isn't it? If the fundamental building blocks of matter are these fuzzy, probabilistic clouds, then why does our world, everything we see and touch and measure, seem so solid, so definite, so, classical? Well, for the longest time, physicists looked at this wave packet spreading as just a weird quantum problem, something that needed to be explained away or overcome. But what if that's the wrong way to look at it? A much more profound idea completely turns this on its head. What if the spreading isn't the problem, but is actually the solution? Believe it or not, way back in 1927, a physicist named E.H. Kennard came up with this absolutely beautiful analogy. He said the spreading wave is like a charge of shot from a shotgun. The cloud of pellets spreads out, but each individual pellet inside that cloud is following its own clear classical path.
So let's think about it this way. A particle starts off as a single fuzzy wave that contains a bunch of possible speeds all mixed together. As it travels, this wave spreads out. But, and this is key, this isn't just random chaos. The wave is actually sorting itself out. It's allowing each of those hidden speeds to reveal its own distinct classical path. The spreading is the transition from quantum to classical. And the really deep insight here is that a quantum wave function isn't just describing one thing. It's describing an entire collection, an ensemble of possibilities. So the spreading we see over time, that's the actual process that allows a single, definite, classical reality to pop out the moment we decide to take a measurement. Okay, so this brings us right back to our microscopic racetrack. We're using the exact same clock in both cases, but depending on which hat we're wearing, classical or quantum, we're trying to do two totally different things with it. And this duality is really striking when you lay it all out side by side. Classically, we treat the particle like a tiny object, and time is just a number we measure to figure out its mass. Simple. But from the quantum perspective, the particle is a wave of possibilities, and time isn't just something we measure, it's an active ingredient. Time is the mechanism that lets the wave evolve and ultimately reveal one of those hidden classical paths when we look. And all of this leads to a pretty profound conclusion. We can keep improving our clocks and our detectors, but that can only get us so far. The true barriers to getting a perfect measurement, they're not engineering problems. They're literally woven into the fundamental laws of physics. And these fundamental limits, they even have names. First, there's shot noise. That's the built-in randomness you get because particles arrive one by one, kind of like individual raindrops in a storm. Then there's back action, which is the unavoidable fact that the very act of looking at something changes it. You simply cannot measure a quantum system without giving it a tiny nudge. So this leaves us with a really fascinating final thought to chew on. We use time to measure our world, right? But down at the quantum level, the very act of looking fundamentally changes what we see. So, what are the ultimate limits of our knowledge in a universe where the observer can never, ever be truly separate from the observed?